how to predict the number of peaks there will be in a carbon-13 NMR spectrum. So in the exam, you'll get a table that looks a bit like this that contains the carbon-13 NMR chemical shifts. So this tells you that the carbon of an alkene goes between 10 and 35 ppm. A carbon bonded to an OH goes between 50 and 65 ppm. And aromatic carbons appear between 125 and 150 parts per million. So let's look at this example. Ethyl ethanoate, the ethyl ester of ethanoic acid. The question you need to ask is how many different carbon environments are there? There are 4 different carbon environments, 4 different carbons. 1, 2, 3, 4. So there are going to be 4 peaks in the carbon-13 NMR spectrum. So to predict the carbon-13 NMR spectrum, we're going to use the table from the data sheet, and then we're going to draw in the lines for each of these carbons. So the first one we're going to look at is the red carbon. It's a carbon, a methyl group, next to a C double bond O, and a carbon next to a C double bond O comes at between 20 and 30 ppm. So we can draw that in like that. The next carbon in the chain going along is the green one. That's a carbon next to an oxygen. And using the table, we can see that a carbon next to an oxygen comes at between 50 and 65 ppm. So we can draw that in. Then the last carbon in the chain, the yellow one, is an alkane type of carbon. It's next to a CH, and an alkane type carbon, so it's just next to another carbon, comes at between 10 and 35 ppm. So we can draw that in as well. So this completes what we think the carbon-13 NMR spectrum of ethyl ethanoate will look like. There are 1, 2, 3, 4 carbons, and there are 1, 2, 3, 4 carbon peaks, all put in the right place for their chemical shifts. Here's another example, nitrobenzene. So it's a benzene with a nitro and NO2 group attached. And again, we have to work out the number of different carbon environments there are. So if we look at this carbon is exactly the same as that carbon. So we can mark those with a similar colour. So this carbon and this carbon are identical. Similarly, this carbon and this carbon are identical. However, this carbon is different from all the other carbons. And similarly, this carbon is different from all the other carbons as well. That means that this has 1, 2, 3, 4 different types of carbon. So we're going to expect 4 different peaks in the NMR spectrum. When we look at the table, we see aromatic carbons, and these are all aromatic carbons, come between 125 and 150 ppm. It's difficult to predict exactly where they're going to come without more information. So we're just going to draw 4 lines. 1, 2, 3, 4. And that's what the carbon-13 NMR spectrum of nitrobenzene will look like. We don't know exactly which one of these is which one of these. So there's the yellow one, that one, that one, that one, or that one. But it's beyond the spec and the breadth of the A-level course to be able to predict which carbon comes there. There are just 4 different aromatic carbons, and so we have 4 different aromatic carbons there. So for the last example, we're going to use this compound, and as before, we're going to work out how many different types of carbon there are. So the carboxylic acid group is one type. Another carbon type is that one there. A third type is that one. A fourth type is this one. another type of this one. This one is also a new type of carbon, and the light green one is also distinct. So for this molecule, there's 1, 2, 3, 4, 5, 6, 7 different types of carbon environment, different types of carbon atoms, whereas for nitrobenzene we only had 1, 2, 3, 4. And the difference is nitrobenzene is a symmetrical molecule. It's symmetrical. If you drop a mirror down there, it's symmetrical. Whereas this compound has less symmetry. And the more symmetry a molecule has, the fewer different types of carbons there are. So, as for nitrobenzene, this is going to have aromatic carbons that are all going to come between 125 and 150 ppm. But it's also going to have this carboxylic acid carbon, and a carboxylic acid carbon comes between 160 and 185 ppm. So if we draw these in, we get something a bit like this.